Hello and welcome to lecture number 21. So in this lecture, we would continue our discussion on BET equation. So today we are going to discuss about the interpretation of the BET equation. So this is the BET equation as we derived last time. Now the constant C is equal to this. So this was also discussed last time. So now if we look at the expression for C, and if we grossly assume that Ka0 is equal to Kai, and likewise Kd0 is equal to Kdi, so that means the rate constants for the adsorption between the molecule and the solid and between the two molecules are same, and same thing valid for the desorption. If we assume that, then what happens, you look at the C, the factor C becomes simply equals to e to the power EAN minus EAL whole divided by RT. Okay, so this is a positive number definitely, and EAN minus EAL, so this difference is denoted as the net molar entropy of adsorption in terms of thermodynamics. So that tells us that higher is the difference, higher is the C value, and shortly we will see that if higher the C value is, the molecules will have a greater tendency to form the contact with the solid and less tendency to form contact with other molecules. So therefore this C, okay, is sometimes taken as an equivalent of a molecular partition function. So this molecular partition function actually describes what is the affinity of the gas molecule to be either in contact with the solid layer, or it would have a tendency to be in contact with the liquid layer. All right, so C actually signifies a type of molecular partition function, just like any other partition function of any solute. Okay, so this is the interpretation of the constant C, and this is one of the most important constants in terms of adsorption. All right, so now let's come and talk to the overall equation over here. So as I told you earlier that for in Langmuir adsorption equation, if you plot pressure versus N, you will get a type 1 shape of adsorption isotherm. But here, if in general, if you plot P by P0 value with respect to N, all right, so the N by P by P0 plot, okay, if we simply plot that, how would the plot look like? So in general, arbitrary, the plot would look like something like this, which is nothing but a type 2 isotherm. So that means the BET isotherm successfully explained the type 2 isotherm, all right, as it is format. So now the question is, if this is type 2, fine, then how can we explain the type 3 and type 1 isotherm from this? Okay, so now let's come to that point. So the thing is, there is an inflection point over here, okay, like that. So if the C value becomes very close to 1, then a type 2 isotherm changes to a type 3 one, and this can be proved mathematically by taking C, by equating C is almost equal to 1, and then you will see if C value goes to 1 here, then these two things cancels out, okay, and so we have a different looking equation, and that would give rise to the type 3. So what is type 3, if you can remember? So type 3 adsorption isotherm is something like this. So now you see BET isotherm successfully explain the type 3 isotherm. So now the question is, how can it explain the type 1 isotherm? So the question is almost here. Okay, so if you look at this curve, so I should draw it a little bit more carefully so that it looks better. Okay, yeah, good. So if you look at this type 2 curve, at low value of p by p0, just concentrate on this here. So this almost resembles like type 1, isn't it? So therefore any type 2 isotherm at a very low value of p by p0 looks like a type 1 isotherm, and mathematically we can prove this from this BT equation. Okay, so let me show you. So okay, so we can understand that how type 2 isotherm is directly obtained from BT equation, and type 3 how it is obtained we can understand. So now let's come to type 1. So as I said, for type 1 we have to test this equation at a very low value of p by p0. So let's assume that the p by p over p0 value is much less than 1. So it is so less that we can neglect with respect to 1. So if we do so, so this equation tells me that we are going to get something like this. So C multiplied by p over p0 divided by, so this is neglected, so and this is 1, and here also this is neglected with respect to 1, so we have 1 plus C p over p0. All right, so p0 is a constant and this is the partial pressure, so this we can equivalently write that this is almost nothing but this, okay, where p is the partial pressure. So you can see that this equation is nothing but this is the Langmuir's form. Okay, so this is Langmuir's, basically this is Langmuir's equation. So the Langmuir's equation means this would exactly give rise to the type 1 isotherm. So you see we can explain the type 1 isotherm from the BT equation where the p by p0 value is very small. So that means at a very lower range of p by p0 all adsorption isotherm resembles type 1. So it starts with type 1 and then depending on the C value and depending on the higher pressure it may go to type 2 or it may go to type 3. All right, so there is also another type 4. For that we will talk about that later. So now there is another way we can obtain type 1. Of course, what was that? That we have already assumed that type 1 isotherm is a characteristic of monolayer formation. Okay, so when the adsorption layer is limited to one single layer we get type 1 isotherm. So from that perspective, can we try to prove that the BT equation reduces to type 1? You understand my point, right? So here we have proved from the pressure perspective, but now I want to prove that from the monolayer perspective. Forget about pressure. So from monolayer perspective, at any pressure, can the BT isotherm prove that it gives the type 1 isotherm? Okay, so for that I have to write one new equation. So I'm going to erase the board and we'll discuss that. Okay, so once again the original BT equation is there. Now we have to remember that this equation was derived by assuming the number of molecular layers are allowed up to infinite numbers. And also I must mention that since I've already mentioned that if C is very close to 1, that means where C value is quite small, close to 1, this BT equation gives the best fit for type 3 adsorption isotherm. Now for a moderate value of C, this stays as type 2. Now the question is, what is the moderate value of C? A moderate C value is somewhat lies around 100. So that means the lower limit of the C value is goes as close to 1, and the higher limit it can go to thousands or few thousands. Okay, so C value remains in between. So anything around 100 is a moderate value, and for that we get the type 2 isotherm. So you can see the type 3 isotherm is really a special case. Now coming back, now if the BT equation is derived assuming the molecular number, the molecular layers are limited to only n, that means a finite number, where n can be 10, n can be 5, n can be 15, 20, etc., then the BT equation takes up in this form. So this is a long equation and I have written it. You don't need to remember it, memorize it, but whenever required you may refer to that. But the main thing is to understand the significance of it. The major significance of this thing, that this has not been derived with by taking number of layers equals to infinity. It has been taken the number of allowed layers is a finite n, and the most important thing is that it can be proved mathematically that if in this equation n tends to 1, that means if n is a if there is only single monolayer, okay, then this equation, then the equation becomes a Langmuir equation. Means this equation would behave as a type 1 adsorption isotherm, and if n tends to infinity, then the equation becomes a BT equation. So that can be mathematically proven. So as I was telling that what is the proof that if we think that the molecular adsorption is limited to one layer, can BT say that can BT equation say that it gives rise to a type 1 adsorption isotherm? The answer is yes, and the answer lies in this equation itself. And this equation is was also proposed by BET, and it was part of their original theory, but I have not done anything to derive this. But this is just a simple result, you may refer anytime you require. But the original BET equation is this. So this happens for some kind of special solids where the infinite number of molecular adsorption is not possible because there is not much space. So that happens mainly for some kind of porous solids. So many porous solids has capillary like pores, okay, channels. So in those channels, due to the limited channel width, it is not possible to stack infinite layers. So the number of molecular layers are limited. So for that we have this equation. And let me tell you, mainly these kinds of solids obeying this kind of equation exhibit type 4 adsorption isotherm. So that's why at the beginning I did not try to explain type 4, because it goes through a slightly different mechanism, of course in accordance with the BET equation. So therefore this situation is applied mainly to explain the type 4 adsorption isotherm. So at the end we will briefly discuss a little bit more details on type 4 adsorption isotherm. All right, so now we can see that how from BET equation we can come to type 1, type 2, type 3, and to some extent type 4. All right, so now let's quickly take a look on that how mathematically the surface area is found out from the BET equation. Okay, so let's do that. So now we come to the topic of the surface area determination, which I have already talked to you to some extent. So this is the linear equation, linear form of the BET equation. And if we try to plot P over P naught versus this quantity, okay, so P divided by N whatever, so by taking this as Y and this is X, so if we can draw that linear form here, so this is Y and this is P by P naught, so it will form a straight line like this, okay, and the intercept, so we call this intercept as I and slope as S. So definitely the intercept I is we can tell it from here, it is 1 over nm multiplied by C, and the slope is equal to C minus 1 divided by nm multiplied by C. Now the question is, I want to know nm because we are interested in nm. This gives us the surface area. So what is nm? Can we easily solve from this? So if we do our maths correctly, the value of nm should come as 1 over slope plus intercept. So 1 divided by slope plus intercept would give us the value of nm. Now the question is, can we find out the value of C in terms of slope and intercept? So can you do the math? Okay, you can try it out yourself. Now two more things I need to say, that is this intercept, the value of this intercept is small, and of course the intercept is so small that sometimes there is an approximation that the slope is drawn, means this line is drawn with an assumption that it passes through the origin, and from that surface area is determined. This is an approximation, but this approximation sometimes holds very good because the intercept is small. So sometimes if you see a BET area has been determined by a straight line passing through origin, you may accept it, so that's nothing wrong in it. Okay, and secondly, the C value has a big significance in determining the surface area. Why? Because the larger the value of the C, the less would be the percentage error in determining the surface area. So experimentally it has been seen that if C value is very small, 1, the BT estimation is not good, percentage error is high, 70, and if C value is high like 100 or even 1000, the percentage error is so small. So for moderate C value, you see around 100, the percentage error is within 2%, which is very much acceptable. So therefore BET model gives almost an accurate model, okay, and well accepted model for estimating surface area of the adsorbents. All right, now the next question is, what is the linear range of BET equation? So are those points stay linear with respect to any values of P by P0? Answer is no. Just like Langmuir one, there is a range. So the range is from 0.05 to 0.35, so basically in the lower range. So so again we have to understand that the BET equation gives best result, best possible fit at lower pressure range. At very high pressure range, the equation may not give you a very good value. So what does that mean? Does the BET equation, is the BET equation failing then? No, not at all, because from this pressure range, BET equation is almost like more than 90% accurate, even not I mean if not 99%. Beyond this pressure, actually not very significant phenomena happens in the solid. So therefore not exactly matching in that higher pressure range is not of a big concern. The most important thing is how the equation behaves in the lower range. It behaves very well. Reason is, the main reason, that because the monolayer formation, that means NM, all right, becomes complete within this pressure range, that means 0.05 to 0.35. 0.35 P by P is 0. So that we have to understand. Now the question is, how do we know that the monolayer formation is complete in such a low pressure? Once again, mathematically it can be proven. How? Now you recollect the original BET equation, n over nm is equal to C multiplied by P by P naught whole divided by 1 minus P by P naught multiplied by etc etc. In that equation, if you put n is equal to nm and then try to solve for P by P naught, so that means what we are trying to do, at what P by P0 value n becomes is equal to nm. So therefore the value of P by P0, P by P0 at nm, if you try to solve it, you would arrive at an equation something like this: 1 over root over C plus 1. So now here you see, the higher the value of the C, P by P0 value at nm would be lower. So in case of the moderate C value, okay, so C value less than 100 or very close to 1 are very uncommon. Okay, so in general most of the time we see moderate C values or even higher. So if you talk about the moderate C value, says you take the C value of 100, root over of 100 is 10, so 1 by 10 plus 1 by 11, you can see that it still falls within this range. And for a C value 1000, you can see that how low the pressure value would be for formation of monolayer. So BET equation tells us that the monolayer formation is complete at a very low pressure. All right, and the higher the value of the C, the pressure would be lower. So that's why the linear range of BT equation is best between 0.05 to 0.35. Now the higher the value of the C, the better is the fit. Okay, so now we next move on to another topic. It's called the determination of single point surface area. Okay, so let's quickly discuss about that, because many times you would come across that point, single point surface area. Okay, so as I have told you earlier that if you perform an adsorption experiment, the equipment gives you a set of volume adsorbed versus P over P0 data like this: V1, V2, V3, etc., and P by P0 data, X1, X2, X3, etc. So it's our job to interpret this data to fit in particular equation to get the surface information. So for example, if we want to know the surface area using BET method, we call this as BET surface area, and we have to utilize that linear form of BET equation, and we have to do the graph plots by taking all those data points, and from the slope or intercept we estimate the surface area. But there is another method that also comes from BET equation, where it gives you an opportunity to find out the surface area without drawing any graph plot, and that method is called the single point surface area method, and that's a quick method, and you can easily do it by just looking at the data. So how is it done? So it is done with one approximation. Now before we put that approximation, let's transform this equation in a bit different manner. So let's divide P naught, we divide by P naught both numerator and denominator of this equation. So it gives us P by P naught divided by n multiplied by 1 minus P by P naught, okay, is equal to whatever the right hand side, 1 over nmc plus C minus 1 divided by nmc multiplied by P over P naught. Now here comes the approximation. So if we assume that C is much greater than 1, so that means if our adsorbent having a C value little bit more than moderate value, that means more than 100, so we can safely assume that C is much greater than 1. So by approximation we can neglect 1 with respect to C, and since C is taken as very big, okay, assuming that more than 100, like several hundreds or close to 1000, C is quite big, so we can neglect this fraction also, because that multiplied by Nm or Vm would be a large quantity, so we can neglect that. So if we neglect that, and if we neglect 1 with respect to C, the above equation comes to P by P naught divided by N multiplied by 1 minus P by P naught is equal to, so P by P naught divided by simply Nm, right? So now from here you see both left and right P by P naught cancel out, so we have Nm is equal to N multiplied by 1 minus P by P naught. Okay, so that gives you the estimation of single point surface area. Why single point? Because you need to find one set of data points from this chart, say arbitrarily this one. So N means V, any one set of data points, so N for this one and P by P naught for this one. So these 2 points would give you a single point surface area. But once again, depending on the value of C, your single point surface area measurement would have some error. So like I showed you earlier, the higher the value of the C, the lower of your error, the lower would be your error. So if you are lucky, if you are dealing with a solid which has a very higher C, your percentage error would be less and you would get good accurate results. So for high C value, we sometimes perform the single point surface area, but for more accurate results we can still use the BET surface area using the graph plot. Okay, so we are almost coming to the end of this lecture, so we would go to our last topic, that is the type 4 adsorption isotherm. So let's discuss that quickly. So the type 4 adsorption isotherm is mainly exhibited by porous solids, special types of porous solid. So let's first take a look. So this is the typical type 4 adsorption isotherm. So I have drawn a representative graph plot. Of course, here I have to plot P by P naught, and here we have to plot the volume adsorbed. So now the question is, what kind of porous solids give a type 4 adsorption isotherm? The answer is any type of non-microporous solids. Okay, so it has pores, but it should not be micropores. So what are micropores? Now depending on the diameter, the pores can be classified into 3 categories: micropores or microporous materials, mesoporous materials, and macroporous materials. And this classification has been done by, once again, International Union of Pure and Applied Chemistry, IUPAC. So they say that those materials that has pores below 2 nanometer, those are called microporous materials, and they, of course, they exhibit typical type 1 adsorption isotherm, and those micropores actually behaves as capillaries, and those materials find excellent application in catalysts. So one of the example of microporous materials applied in catalysts are the zeolites. Okay, so those are naturally occurring minerals that are having micropores. And then mesopores. So the mesoporous materials that have pores range between 2 to 50 nanometer, and so in this region you can obviously multiple layers of molecular adsorption is possible, but that multiple number n is finite, not infinity. So these are used in catalysts, drug deliveries, and biosensors, etc. And then we have macroporous materials that have pores more than 50 nanometer. Practically those are of not much interest, but some macroporous materials can be used as catalysts. So overall, So these two categories, that means mesoporous and macroporous, are termed as non-microporous solids, and they typically exhibit type 4 adsorption isotherm, like I drawn here. But there is one characteristic features of those typical type 4 adsorption isotherm, that this is often associated with a huge loop, and this loop is called the hysteresis loop. So look at here. So usually, so this is called the adsorption arm. So that means when the gas is adsorbed, it will follow this pathway until up to a very high pressure, and after that, when pressure is lowered, the desorption process would follow. Usually for all other types like type 1 or type 2 or type 3, the desorption arm retrace exactly the adsorption path, but for type 4 it often deviates. So that means when it gets desorbed, so it retraces up to a certain point and then it deviates, and then it forms a loop like this. So this is the desorption arm here. So this is the adsorption arm and this is the desorption arm. So this loop is called the hysteresis loop, and oftentimes in porous solids, means non-microporous solids obtaining exhibiting type 4 is associated with large hysteresis loop. The question is, why does hysteresis loop appears? There are quite a few theories, but for this course I'm not going into the details of those theoretical model. But in short, we can tell you that the best theory that is accepted so far to explain the appearance of the hysteresis loop is called the capillary condensation theory. Okay, so the capillary condensation effect, so once again it is associated with formation of capillary meniscus and Kelvin equation, etc. So I'm not going into that, but remember, so the capillary effect or capillary condensation effect is responsible for appearance of the hysteresis loops as it is generally understood. Now, once again, as I have told you earlier also, that BET model explains some part of the type 4 with certain pressure range, of course. So it is not possible to mathematically fit the entire range of the type 4 adsorption isotherm, and there is no best theory so far that can explain all the adsorption isotherm in all pressure range. Whatever the available theories are there, out of that, BET gives by far the best result. That's why BET theory is widely accepted. Okay, although it is not 100% accurate, but it is widely accepted. The main reason, it provides a pretty accurate estimation of the surface area. So when it comes to the estimation of surface area, BET equation gives by far the best results. Why? Because it is estimated as a very lower pressure range, and in the lower pressure range, as I told you, if we have a moderate value of C, the BET theory just rules. Okay, so this is all about the adsorption of gases on solids, and I have explained you two more most important theories, that is the Langmuir's adsorption model and BET adsorption model. And the details of the BET theory that I have explained throughout two continuous lectures, you may not find it any textbooks. Okay, so I hope these video lectures would help you not only in this course but in future when you go to do research, and especially when you do your study in a more specialized fields like materials chemistry or porous solids applied for catalysis or drug delivery, etc. So this is all about the course so far, and I hope you enjoyed these video lectures, and then it's your turn to study, and if you have any questions, so you can reach me anytime, and so I will see you later some point of time, and you stay safe and take care of yourself, and thank you for listening. Goodbye.